So without further ado, I want to introduce our CEO, William Falcon.
Hello, everyone. So who's a StatsQuest fan? I've been for many years. Yeah, great. If you haven't watched it, please find his videos. They'll teach you all the stats you need to know. So, first off, before I get into all of this, I just want to thank the whole team and everyone who's here. Thank you all for showing up as well. Thank you for being part of the community and supporting us from day one. Everything you're about to see was many years of really, really hard work, a lot of hours, a lot of weekends, a lot of nights, but we're here to hopefully share that with you. Just know that this is stuff that we've been working on for a long time, and it's honestly just been really difficult to figure out how to do it correctly, the Lightning way, in a way that you don't have to think about it, in a way that it's just intuitive for you, right? So I think we tend to build kind of big things less frequently instead of just releasing a bunch of small things really fast, right? So I just want to thank the team for doing this, and yeah, it's been a great journey. So hopefully we share with you today, and you can join us for the rest. So first up, I just want everyone to meet Dan, and Dan Biderman is a PhD student at Columbia University. It's actually the lab where I started learning about deep learning as well, many years ago. And we're going to hear a little bit about Dan's work.
I'm a PhD student here at Columbia in the Mind, Brain, and Behavior Institute. I work in John Cunningham and Liam Paninsky's labs, which are in the statistics department. And I'm doing a lot of work on estimating animal movement and behavioral sort of variables from raw videos. In neuroscience, a huge goal is to sort of link neural activation with actual, meaningful, rich behavior that certain animals, or as we call them, model organisms, are doing. And over the last few years, there's been a huge revolution in our field trying to use videos to actually record what the animals are doing, and then use a variety of deep learning, computer vision, representation learning algorithms to try and extract information from these videos. But what was missing until this point was algorithms that are actually targeting the behavior of the animal. And when I started here, we started asking ourselves, what can we do with actual videos of animals, and what can we do with the most modern computer vision algorithms to help us with this? Pose estimation problem is one that has been studied extensively in computer vision and graphics, and is being used a lot in autonomous driving, for example, identifying pedestrians, predicting where they will go. But now the challenge that we are tackling in many other labs is we're sprinting very hard on our machine learning paper, trying to submit it to one of the big machine learning conferences, trying to polish, the proofs and the algorithm and all of that, and analyze performance. But another month could look like sitting in an actual lab with someone who is running experiments, trying to set up certain analysis pipelines with them, trying to understand maybe which new mathematical framework can explain some of their findings. So when I heard first about PyTorch Lightning, I immediately fell in love with it because everything made sense. The idea that someone would take care of all of the stuff that we were already doing, like looping over, the iterations of training the model. And then when I got into it with this pose estimation project, I really fell in love with the idea that everything here makes perfect sense.
Okay, so a lot of neuroscience research happens at this lab, many other labs across the world as well. And surprisingly, there's a lot of deep learning involved. So I really encourage you to check it out. So this is another one of our kind of featured apps I will show in a minute. But Nyla, so meet Nyla. She's also coming from NVIDIA as well. And this is kind of some of the work that this team is doing. So this is Omniverse Replicator. And I encourage you all to search on this on YouTube. And we wanted to show you a little bit of a clip. So Omniverse Replicator, basically what it does is it allows you to simulate synthetic data, right? So you can generate samples when you don't have enough data for something. A good example of this is if you are a something like Amazon, and you have a camera and you're kind of sorting packages, and then you change something about the package or the label that might break the model, right? So you could actually take all that packaging and then simulate it in Omniverse, in VR, and you can actually generate the samples there and then retrain the models, and then hopefully they translate to the real world. So there are a lot of really cool applications that you can use this for. And yeah, I encourage you to check out this work as well. And meet Mark as well. So Mark is coming from Mars, and I want to show you a little bit about his work.
Pets play an important role in our lives, but sadly, 1 out of every 4 dogs is going to develop cancer at some point in their lifetime.
Let me give you a quick overview of the inference pipeline. The biopsy is placed onto a slide, and a scanner converts this into a digitized image. We leverage torch vision to build the count or no count classifier, which is trained with thousands of examples labeled by the pathologists, and the size of mitotic figures should be counted based on whether there is cancer present in the image. The algorithm then detects where the edges of the tissue are on the image and removes the background to improve efficiency and accuracy. The image is then broken down into smaller images, and a team of fully convolutional neural networks predicts for each pixel if they belong to a mitotic figure or not. A morphological filter removes any marked pixels that do not belong to a mitotic figure by filtering for size, color, and shape. We then analyze all of the locations of the identified mitotic figures to find the region of greatest density of mitosis. These findings are then available for pathologists to access.
All of these 3 projects that you've seen have something in common, which is that a lot of this has been worked on with Lightning, and we'll go into this work a little bit later. So first, I kind of want to step back, and I want to talk about some of the things we've done in the last few years. Really, in 2019, we introduced the notion of, as you saw in the previous code, the notion of kind of the trainer, and we basically have made a lot of the things that the PyTorch team has built accessible to a lot more people, right? So before we move into that, I do want to thank the PyTorch team, and Sumit is here, so if he wants to stand up and just shake his hands. Again, a lot of the work that we've done is really make a lot of this stuff usable. And one of the ways we've done that is by introducing the trainer, right? And this trainer is a really good paradigm that has actually spread into many other parts of the ML world. And I think it's working out really well. So we've been really excited to just be a part of that movement. And it's really had this paradigm shift where we've seen that it's kind of something that you need to actually unlock scale, right? I think everyone really wants full flexibility, and it's great, but full flexibility makes it really hard to do scalable work and to have collaboration, right? So you need something in between. And then something else that we kind of introduced a few years back as well is PyTorch had introduced XLA into the framework, and it also had introduced multi-GPU training and all this. But you needed to basically recode everything to switch between all of them, right? So we introduced this notion where you could literally just change accelerators. And we rolled this out, I think, September 2020, I want to say. And suddenly you could, train on GPUs and TPUs and all of that, and it's worked out really well. And again, it's a pattern that's becoming pretty ubiquitous across the industry as well. So that's 2019. And a lot of this came from, I just mentioned Dan was at Columbia. I was, doing computational neuroscience there as well, and at the time I was working in Theano, which was a great framework. If you played with it, it is very, very hard to use and debug, but nevertheless, it was helping us do what we needed to do back then. And we were training models. We were basically doing experimentations where we were trying to reconstruct what a retina saw, right? So we could flash ImageNet images on this retina and capture the neural activity, and then use, back then, an autoencoder to reconstruct what the retina saw. This is an application for prosthetic retinas if you have some sort of degenerative eye disease. Now, that training was taking probably about 30 days for one epoch of ImageNet, and we needed to run through a few hundred of those. So I was not going to spend 2 years waiting for that thing to finish, right? That was just one experiment. So what I did was basically bought a bunch of 1080s, kind of like what any student would do, built a machine with 4 of those, and then rewrote the code into TensorFlow, which was great, and basically got that down to about 23 hours per epoch. And we were able to publish at NeurIPS that year, which was great. My first paper, very spoiled, never happened again, but it was a good time. And then a few years later, when I ended up doing my PhD at NYU, and then I was at Facebook AI Research, we were trying to scale up, same problem, honestly. It was trying to scale up training on the Facebook cluster. We were doing a lot of self-supervised learning back then. So back then, we were just trying to scale that up. And this was taking, even on the Facebook cluster, which had a massive data set, was taking months to train. So that's where I started working a lot with the PyTorch team that was there, Mile from FairSeek as well, Steven from Parlay, a lot of really great leaders in the distributed world. And through the free times that they had, I was able to pick some tidbits and embed a lot of that knowledge into Lightning, where we finally got the training down to about 1.5 minutes per epoch across 512 GPUs, right? And then we were doing like 8 models at once, which was more compute than you should be using. But nevertheless, it was cool. So a lot of the scaling came from that as well. And back then, really the vision was to have kind of every company in the world and all the AI labs to basically take all the collective knowledge that they had and put it into a single place, right? And I think during that time, you had GitHub repos that had these really cool small tricks, but no one had access to them. It was like, unless you were at like Google or Facebook or some crazy lab, you probably didn't have access to stochastic weight averaging or gradient checkpointing or something, right? You needed to know that you needed to find it. And so what I wanted to happen was that all of that knowledge could be centralized in one place so that everyone could have access to it, because I was fortunate enough to be at that place, but I had been in a position before where I wasn't, and it was really hard to access. So I think what ended up happening is, when I left Facebook to focus on this full time, this is kind of the growth that Lightning had at the time, right? So we were seeing about 25,000 downloads a month, which is great. So back then I was like, okay, awesome, like the vision has come true, and now this is a collective place where everyone's being able to benefit from it. Now, fast forward 2 years later, and we have over 4 million downloads a month. So it completely blew my expectations, right? Like, yeah, have no words, right? And this is really, a testament to the community and everything that we've built. Again, this has really been a collective team effort by everyone in the community. But today there are thousands of companies that are using Lightning to basically work with PyTorch and scale what they're doing, right? So inference, deployments, it's gone beyond just research at this point as well. Now, if you look at the community, and if you're on Slack, if you're not, I invite you to join, you will see that people are working on all sorts of things, right? Everything from research to inference to finance to healthcare. So all of these things are represented, and I think what's really cool is that Lightning has really become a framework that is not tied to any one particular domain. It really does let you do any of those domains. And I remember at first, the first team to adopt this stuff was kind of researchers inside FAIR, and then it kind of spread from there. And always the question was, can it generalize to my particular thing, right? We're all researchers, and our work is obviously so special that it could never be generalized to a framework, right? That's what everyone thought. And maybe you all think that until you actually try it, and you're like, oh, it turns out that it is right. I can actually refactor it, and I don't really lose the flexibility. So, it was the too good to be true argument that took us about 2 years to kind of show the world that it is not too good to be true, right? Now, when Lightning started entering industry, in research, there are certain things you do that you're never going to run into. But once you start going into industry and actually putting things into production, you start running into issues like needing feature stores, right? Like needing deployment strategies, needing, Redis cache, reading databases. So it's extremely difficult to get a lot of this stuff working correctly. So the model part of it it is easier because collectively we've all made it a lot easier today than what it was before, but it just means that everything else has become really difficult as well, right? So the model itself is no longer the hard thing, which is good actually, but everything else is hard. The data pipelining, the deployments, the retrainings, like how many models do you have, how do you switch them, red, blue, all this stuff, right? So I call this a fragmentation problem. And the fragmentation problem is not really unique to AI. It's just unique when it happens when a field grows, right? And AI is, as a research field, has been around for a long time, but it's just recently started to get in the industry in the last few years, which means that we're seeing problems. So if you think back to the automobile, when the first cars started coming out, you basically didn't know you needed seatbelts. You didn't know you were going to have a radio. You didn't know that you could have an electric engine. As the technology matured, we discovered that there were a lot of things that we needed to make this platform work, right? And so you started having many, many different ways of doing one thing, right? So in the car example, you might have 50 different types of tires, and that's great. And you should have this flexibility. But you need a platform to make it all work, right? If you don't have a standardized platform, then the tire makers won't be able to kind of interoperable, like they won't be able to interop between different platforms. So you need something where a lot of these things can fit in, different wheels, different types of engines, different types of radios, and so on. So once you had this kind of platform, it really unlocked the ability for the automobile industry to kind of scale beyond where they were before. Again, it happened with computers, right? So everyone had kind of their own way of doing things. There were really no standards. You know, if you built your own machine, how many types of RAM are there, right? So there's hundreds of these. Now, you could not have this flexibility to put in your own RAM if you didn't have, again, some sort of platform that allows all this stuff to work together. So these are just two examples, but if you think back to any new technology, you're going to have this cycle where at some point the thing becomes super fragmented and you need a way to make it all work together. So remember, we started basically trying to solve this fragmentation problem a few years back, right? Which is really hard to do. In 2021, we basically solved one portion, just a small part of it, which is trading at scale, right? So we introduced Grid, where you can train TensorFlow, Keras, anything you want at scale. And this really solves kind of like the tooling problem of, okay, I need interactive notebooks, the GPUs, I need to run experiments, all this stuff, but it doesn't solve deployments, it doesn't solve you know, where are my checkpoints? You have questions like, okay, the training's done, which is the best checkpoint? What if you want to use an experiment manager? Which one? How do you swap them up? So this is really, again, for us, it was kind of a first step to solving the bigger problem that we wanted to solve, which is how do you make all these things work together, right? So this is really what the goal has been from day one. Again, I said it's been about 2 years we've been trying to solve this. And it's actually really difficult because today there's a big status quo in the world, right? DevOps came, so some engineers came from the DevOps world, and then they took all those YAMLs and all those DAGs and all those things and turned them into something called MLOps, right? Which is great, except that none of us care about YAMLs. None of us care about Kubernetes, right? Some people do, but the people who are doing the research and the people who are building the models and the people who are doing, you know, the fraud detection, that are doing kind of the industry applications, they just want it to work. They don't care how it's being done. If monkeys are managing your machines, great, as long as it works, right? So the status quo is really hard to change. And so we are basically going to look at how the product that we're going to introduce today would have been built if we just followed the status quo, right? If we just continued to think how the industry is thinking today. So the first thing that would happen is we would introduce a DAG framework, right? We love DAGs, why not? So first thing that we would introduce is this. Then we would have some sort of workflow scheduler because why not, right? You need a way to schedule that stuff. Then we would introduce a way to do infrastructure as code, or maybe give you like a really cool YAML generator or something like that, right? Then we would have some sort of framework to build ML-powered apps. Like, what even is an ML-powered app? What does that mean, right? Then all of these tools have a UI, right? You use await some biases, use comment, whatever, they'll have the different UIs. So how do you connect all of them together? And then finally, you need a way to collaborate because, yes, you may be working alone right now, but I promise you the second that thing goes beyond POC, you're going to have collaborators, and it's going to be really hard to do what you're doing. The way it would work is we would probably specify a function. And then we would just add a bunch of decorators. First, we'd define a node on a graph, and we'd say, cool, this is my first thing. Next, we would say, schedule it every 12 hours. Then, we're going to give you some sort of admin access, because maybe some people should have access to this or not. And then we're going to specify the hardware, right? This is how the world would build this today, and no one would question it, right? Then you'd have some beautiful UI like this that shows you a DAG workflow, and you're like, oh my God, this is great, I can debug it. And then maybe someone would even try to build you a UI that you can drag and drop and connect things. Like, it doesn't work, guys. It's not realistic. So we're not going to do that, obviously. This is not the Lightning way. So we're not going to do 6 things. We're going to introduce a single thing that does all of those things, right? Which is a very difficult thing to pull off. So we're going to show you how we've done it, and also convince you that it is not too good to be true, because I know that's what you're probably thinking right now. So that's Lightning AI. And this is really the operating system for AI. It's really the first operating system for AI. And I really today think that this is at least 2 years ahead of anything that's out there, because it has taken us a very long time to figure out how to make this in a way that you do not have to think about the infrastructure, you do not have to think about how things are happening, and it's really just a way to reimagine how you're going to build AI next. So what can you do with this? You can do a model development project, sure. String together a framework, grab some databases, experiment manager, mix them up. You have one of these. You can do an ETL lab. Doesn't even have to have a model in there, right? This is just straight up data pipelining. It can really be anything you want. So let's talk about the complexity of building systems today, right? Today, this might be the perceived complexity to build an ML demo. Okay, you publish a paper or something, or you build something new, and you want to show someone an interactive UI to play with it. Great. That is really not complex compared to a real production system, right? That is not a production system. A production system has a lot of moving parts, different environments, environment variables, fault tolerance, right? Local debugging, system observability. Like, when things fail, how do you monitor that, right? So with what we're introducing, we expect this complexity to be able to be unlocked, right? Because now you don't have to deal with a lot of that stuff. You'll be able to build much more complicated systems that really kind of the enterprise world has been bottlenecked today, because we've had to build with DAGs and we've had to build with YAMLs and so on, right? So I know it's too good to be true. So let's go ahead and look at some of the work that we've done today and show you some of these Lightning apps, right? So the first is going to be the app from the Omniverse team. And this Lightning app, basically what it's doing here is it's going to use, so what you're seeing is the UI of the Lightning app, right? So this Lightning app is actually available on the gallery, which I'll talk about in a minute. And basically, you can drag and drop 3D assets into this. So if I've never worked with them, but apparently there are these .usd files and so on. So you can drag these guys in. And then this is going to basically, you're going to be able to compose a scene, right? And then once the scene is composed, you're going to basically ask the Omniverse Replicator that's running on an A10G on the cloud to simulate this data, right? And this is going to start generating the actual simulation. So here I'm just composing the scene. And what it's going to do is you're going to give it some parameters, kind of like transforms, and it's going to like flip the image and do a bunch of different things. So this data set's being generated on a machine while there are a bunch of other models training on other machines that are training on this data set that's being generated, right? So this is a full pipeline. This is like create the data set, sample it, train models, retrain all of this, all in a single app, right? So let's hear back from Dan, and we'll hear from the app that he built as well to do his work.
So everything we're doing in machine learning research is basically thinking about models, sometimes thinking about the inputs and outputs to these models, but we deal with these models, we refine them, we obsess about them, we write papers about them, but once we're done, the models are sort of dead. We assume someone else may use them and to do something with them. But the reality of things in academia and science, but also in industry, is that a model is only a part of some pipeline. And usually, as they say with kids, it takes a village. Here, it takes a whole company to build an app. You need DevOps engineers, and you need data engineers, and you need the researchers that do the science and machine learning engineering. So we sort of specialize into different components of the pipeline. Each is doing one thing, and we're not seeing the big picture. And in science, often it's very rare to see applications that are starting from data curation and are ending with actual deployed system. It's very rare to see this even in the biggest consortiums in physics. Sending off a model to train on the cloud, you may not have the infrastructure locally to train a big convolutional network. And then after the model is being trained, you can diagnose what happened, see those images in 51 or the logs of training in TensorBoard. It's a standard computer vision pipeline, but for us, the actual application is say animal pose estimation. A pipeline starts with curating data, getting a bunch of images and annotating certain things about these images, like body part positions, or like if it's a dog or a cat or whatever. And then from there on, you need to take this data and use it as a training set for your model. You need to train your model, and then you want to do stuff with the model. First of all, see how it did in training, but also predict on new data or whatever. But usually these different segments are separated, and you have different scripts that do each of them, and it all sort of depends on some human in the loop that will try to trigger these events. But actually just chaining them together in one big operation that allows people, without local installations and without a zillion SSH tunnels and all that, allows you to label data, train a model, get the results back, predict things, wait for new data. That's on the engineering side of things, that is something that's almost impossible to do on your own as a researcher.
So I want to emphasize that. So Dan's app basically does all that he just described, and he's a PhD student. He's not 12 ML engineers, right? He's not $10 million in 2 years of work. It's one person that can do all of this work, right? So I know, again, this sounds a little bit crazy, so I want to show you the code. And if you go in the Lightning repo today, you're going to see a few abstractions that are coming in. First, you can now import Lightning as L, because now we're allowing you to go beyond just training models. You can now deploy and build full applications, full end-to-end ML systems, right? So import Lightning as L, you have the Lightning flow, right? So we're only introducing 3 abstractions: Lightning flow, Lightning work, and Lightning app. That's it. So you still have the Lightning module, the Lightning trainer, Lightning flow, Lightning work, and Lightning app. So if all you want to do is build apps, you can do that. If all you want to do is build models, you can do that. If you want to build models and then do something with that, you can now do that as well. So again, it's exactly like the Lightning module. You have an init where you're going to define what you're going to do with stuff. You have a run. This basically replaces training step. It's exact same thing. But this is for your whole pipeline, right? This is what would be a DAG, usually. It's not. And so let's walk through this. So first off, you have this drive here. So this is a distributed file system where you don't even have to think about it, right? So there's no more like, where's the checkpoint? Can you move it from that machine to this machine? Where's the data? Blah, blah, blah. No, just create a drive. That's it. This thing can be multi-cloud. It can be support your on-prem cluster and a multi-cloud thing. It's all fully abstracted away. So this is your basically data pipeline part of it. So we're going to use scale for data annotation. Notice that you have environment variables, right, that you can pass in. This will work on your local machine and on the cloud as well. And you pass in, basically you have the project name. So these are settings for these tools, right? Snowflake, so we're going to take the data once it's annotated, then we're going to put it into Snowflake, then run it through Databricks for feature extraction, and then we're going to store the features in Tecton. This is the model part. We happen to be using PyTorch Lightning here, but you can use anything, right? You can use Keras, you can use TensorFlow, you can use PyTorch, you can even use just regular Python scripts, right? Whatever you want. And then we're going to monitor with Comet in this case. Then we're going to deploy. Deployment is going to happen with OctoML. I mean, this is a very complex system on purpose, right? OctoML is going to take the weights and optimize them for the hardware. So if you're deploying on GPUs or edge devices and so on, then we're going to actually do the deployment in SageMaker itself, and then we're going to monitor this with Arthur AI, right? So how does this actually work? First is we have this event loop, right? So this moves us beyond DAGs. DAGs are not Turing complete, right? DAGs, you cannot for loop, you cannot if statement, you cannot while loop. Here, it's just Python code, right? This is just Python code. So under the hood, what's happening? You have this kind of event loop. If you've been like a React developer or mobile developer, you're kind of familiar with this model, right? So this is actually coming from the mobile world and the application world. So this is happening. So the first thing that's going to happen is we're going to kick off this data annotation. And this could take a whole month just sitting there. So this happens. This is false, 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 and you're good. So the loop continues, continues, continues. At some point, you have enough annotations. You have 1,000 of them. And then you kick off your data pipeline, right? So this happens. You fetch the data. Here, you transform them. And then you put them in the feature store. This is what would normally be like a DAG, right? Data pipeline. Actually, let me just go this way, right? So this is the data annotation part. This is basically the DAG. And then here, you have the continuous retraining. I know it doesn't look like it, but literally 3 lines to do that. So whenever you have a new feature, this could have taken a few hours to get this pipeline done. When this has new features, you're going to kick off this training run. So this model is going to start in parallel. Notice this is a non-blocking call, so it's going to happen in the background. And then this is also going to kick off the experiment manager as well. When you have a new checkpoint at some point, again, could be hours, could be days, doesn't matter, you're going to now do the deployment optimizer. You're going to send the weights through this API to Octo. They're going to send you back new weights. Then you're going to do the deployment here. And yeah, I guess you refresh the deployment monitoring here. So continuous retraining, continuous redeployment, data pipeline, data annotation in like 20 lines, right? Obviously, the complexity is in these components, but the app itself takes like 30 minutes to build. And it really just strings together what you already have today. Now, all of these tools have their own UIs. So let's, again, just like Lightning, this is not configure optimizers, this is configure layout. You can actually just specify the whole UI here and say, okay, I want my app to have 3 tabs, and in each tab, I'm going to render each component. Each component here has a self-contained UI. So you can get these components from the open source, and they will have their own UI of what they're going to show for you. So, Comment has a UI, Tecton has a UI, Arthur has a UI. So you get the page for your app, right? And you're able to basically click between them. You can add your own UIs afterwards, right? Which will show you another real apps in a few minutes. You can add more. You can add React UIs. You can add Angular, Vue, Streamlit, Gradio, whatever you want, right? They can all work together. You can have all of them working at once together, which is wild, right? If you want to do multi-cloud, great. Sounds good. Just go ahead and use this cloud resource, specify the cluster you want to go on, and you're good to go. So I can train on AWS and deploy on GCP. If you're in research, why do you care about this? Because it's cheaper. It might be cheaper prices on different clouds. If you're trying to hit a paper deadline, yeah, your cluster's probably not going to be available, so you could probably train on the cloud. Again, one of the apps that we'll show in a minute lets you search within videos. This is what the UI looks like for that app. It's built with Streamlit. Again, I believe we have a React version as well. But under the hood, this is a distributed system, right? That you just can't tell. And the PyTorch Lightning model itself is training across a few machines. There's a YouTube video extractor that's on a separate machine. And there's a Streamlit component that's rendering the UI on a separate machine. This can even go beyond multi-cloud, right? And the UI still just appears simple. So don't let the simple appearance of this hide the fact that this is a very complex distributed system under the hood. So I want you to think about it this way. You have the iPhone, which is the hardware, right? Grid, which is now called Lightning Cloud, allows you to connect clusters together. It's really just that. It's a kind of equivalent to hardware, but it's really multi-cloud hardware. For that, you need an operating system to be able to build and run apps, right? So on iPhone, you have iOS. Here we have Lightning AI, where you can build iPhone apps, and you can build Lightning apps as well, right? So again, a Lightning app is an end-to-end ML system. It can be as simple as a demo, literally, just like a Gradio UI, or it can be as complex as the app that I just showed. this is the Lightning platform. And yes. And so part of what we're releasing today is Lightning.ai, the new home for the Lightning community, which Eden will talk about in a few minutes. And this is where a lot of the open source apps will go. Everything we do is open source. So all these systems, you can put them into open source. So if you want a recommender system that's like would take months to build, you can just go clone and run this in 2 minutes, change some code, and you have it running, right? Very, very quickly. Then you also have components, right? So the Lightning app is made up of components. This thing has a few components in it, BigQuery, I don't know, Databricks, all these different things, right? So these are also all open source, which means you can take the serving or literally a component to spin up a Jupyter notebook or a serving engine and drop it into any application you want. So even if you're just building research and suddenly decide you want to, I don't know, show a demo or actually build a product from it, or you find someone's research that is exciting and you want to build a real product around it, you can now strap on all the data components, the databases, the feature source, all that stuff, and then grow from there, right? So all of this lives under our new page, which is lightning.ai. So I want to hear back from Dan about, let's see, where are we? Okay, so we have a small video to play for you guys. And I just want to drive home this point that you have the ability to do a lot more than you could today without needing $20 million, 2 years, 200 engineers to build something that 87% of the time is actually never going to see the light of production, right?
Working with Lightning AI now allows us to have an actual product, not a model, but without having the entire so-called village you need to raise a product. As academics, as scientists.
Yeah, so like you said, you don't need a village or a whole company to build this stuff, right? It's taken us a whole company to build this and many years to think about it. And what you've seen today is not something that could have ever been built by any single one person, right? True tech innovation cannot happen at the individual level, ever. It is really hard to pull off because you need the experts across Kubernetes and infrastructure teams and frameworks and applications to all work together in a single cohesive vision and make that happen. And that's really where you can leapfrog technology, right? This is why we're not introducing a incremental advancement to some sort of DAX system or something like that. We're introducing a completely leapfrog product that really unlocks a lot of different possibilities. And this could not have been possible with the whole team working together, but really it's the whole community as well, right? And how we envision the community and how we look at the community is we're all working together. That's it. Right? We code with you, we help you solve bugs. I'm on Slack answering your questions, everyone else is as well. So we're on this together because we can build this next generation platform, right? Like what we've done is taking care of a lot of that hard work to really empower everyone here to build the next thing. So think about Apple, right? When Apple launched many years ago, some of these apps are billion-dollar companies. Just some of these apps, the Ubers, the Snapchats, right? These things became giant successes because they had access to a whole community, a whole set of users, access to marketing, access to a lot of the stuff that we provide for the community today. So, although we're only launching with 20 apps today, which happened to be built in the last 2 weeks, all these apps, the question is, like, who's going to build that next app that's really going to kind of push the boundary of what's possible today? Go beyond the systems that are built today, right? And this is what we're inviting you to do, to build with us, to take the platform that we put together for you and create the next crazy multi-billion-dollar company. Like, you have the ability to do that, and you don't have to be an expert in ML engineering anymore. So thank you all for coming, and I hope you enjoy the rest